All right, well, thanks so much for the invitation. It's been really fun to watch the Breathe sort of consortium, if I don't know if you're calling it a consortium, but grow, and all the interesting work that's being done, all the interesting research that's being done that's relevant to the goals of Breathe. So I always like to start with acknowledgements because I usually don't get there at the end. So these are all of my research group over the last many years that have contributed to this work. Those that are underlined have contributed the most to what I'll be presenting today. And been fortunate to have funding from all these sources and excellent collaborators and contributors, including Will. So, I saw this one time and I had to steal it because, we talk a lot about fires and fires means for us smoke, right? And really it's the smoke that we're interested in understanding a little bit better from a chemical perspective, and being able to do some predictions around smoke. So these are some images that were associated with this a really bad fire season. This was 2020. And what we see on the right is PM levels, or sorry, this is not PM levels, they're air quality indices measured by these purple air monitors. And what we also can see, so we can see these hot spots, right? These, big red hotspots indicating poor air quality. And then on the left, in sort of the satellite image, we can also just see the smoke blanketing the West Coast. But when it comes to protecting human health and thinking about what we can do about this, we have to dig in a little bit more. And so smoke really is a complex mixture of gases and particles. And so what we're used to seeing these billowing sort of smoke clouds, and we can see that this dark color, this represents the black carbon, right? This carbon is absorbing this light. We also see this brownish carbon, and then we see a lot of white, which is the organic carbon. And then what we can't see are all, a large amount of trace gases. And the color here and these different parts of the smoke, they actually represent the composition. And this composition really influences both the health and the climate effects. And again, we're interested also in these gases that can't be seen. Another thing that I just wanted to mention is that, we're often used to thinking about megafires, right? These fires that burn in California that often burn for a couple of days. But in the context of health effects, we also sometimes have fires burning for very long periods of time across the Western US and other parts of the world, really. And so just to put some numbers out there for you, between the period of 1973 and 1982, fires burned on average for about 6 days. This is data put together by Leroy Westerling. And in the period of 2003 and 2013, these fires burned on average 52 days. Now, some of this, of course, is that we want fires to burn for longer when they can, to control fuel loading. So there's reasons for this, but again, we need to think about the health implications of this. I don't have to go through this part, what the health and the long-term the short-term and long-term health effects are. But also, again, we deal with visibility degradation related to smoke. So these are all of the types of concerns that we have with smoke. Another thing that I wanted to show, this is some data that was sent by one of my collaborators, and I thought it was really interesting because I was in Colorado during the time that this shot to the right was taken. And so this isn't still in 2020. And I kept being woken up at about 4 or 5 in the morning, just this really intense smell of smoke coming in the windows. And you couldn't see smoke anywhere. You couldn't see fires anymore. But here he said, oh yeah, this happens all the time in Montana. And here is some data that I took outside my outside my house. So basically these PM2.5 concentrations shooting all the way up to 600 micrograms at about 6 in the morning, and then dropping down. And so this, of course, is probably meteorology, but is being influenced by chemistry. And so at the end of the day, we're interested in understanding the chemistry and the meteorology that control the spatial and temporal distribution of particles. So from my perspective, I often think about what happens to particle mass, and I'm going to focus on that organic carbon, that white part. And the reason is because even though, that black part catches our attention, the black smoke is only about 10% of the mass emitted from fires, where the organic compounds are about 90% of the mass, plus a reminder of all these gases that we can't see that are organic carbon. So that's what we focus on in my group. So with just the dynamics, in time, that particle mass will go down in time and space. But due to chemistry, we actually get the growth in particle numbers over time. So depending on where you sit, depending on meteorology, you may experience, different levels of PM over time, depending on where you are spatially. When we track a plume in the atmosphere, what happens is that we see that particulate mass, OC, kind of just follows this narrow range. And that's really because there's a competition here between the dilution and the dynamics, okay? And so what's happening is that there's a chemical conversion of the gases that we don't see to particle phase of organic carbon. This changes the mass concentration, composition, and distribution of PM. And again, this is really what influences the health and climate effects. These are poorly constrained. They're challenging to capture in air quality models, and this has really been the focus of my work. So what we've done is we've collected samples in all kinds of platforms over the last many years. So from the Fire Lab, we've been up in Blodgett Forest several times. We flew instruments on the Twin Otter and on this mobile lab during wildfire season. And I'm just going to show you some results from our analysis. So we use two-dimensional gas chromatography, and this is where that fingerprinting comes in. So what we see are the distribution of those gas phase compounds. And there's a lot going on, and you really don't need to see the details, except to say that we see different patterns in these chromatograms. And these different patterns tell us that the chemistry of these emissions is going to be different, okay? And that the pollutant information from these emissions is going to be different. And we can also see that it's not just, so here we have black spruce, and if I showed you something like an agricultural crop burning, it would look completely different. But we also see differences between different parts or fuel components. So this is an example where this duff, this downed material, couple layers on top, has a really different emissions pattern than like when we burn canopy. These are lab-based burns. And so this is one of the findings from all of the data that we've been looking at, is that we can sort of start to fingerprint and then start to say, okay, what differences are we seeing here in the different kind of fuels burning and different components? And so this is just a little bit more about that. So the height of these bars represents a total emission of one compound class that we're interested in. And I've just shown you, so we can look at shrubs, we can look at things like grasses and peat, lumber. And then we can also say that even within this class, so even when we look at something like conifers, when we look at the canopy versus the composite, we see different heights of bars, right? This tells us that the amount of emissions are different between these different elements. So different between the canopy, composite, and the litter. And so this is really interesting from a chemistry perspective, but it really got me thinking about emissions are different as a function of these different parts of what's burning. Well, these are going to be different between prescribed burns and wildfires. And does this actually start telling us something, that maybe the emissions from wildfires are actually different than prescribed burns, right? Because you're burning different components when you burn a prescribed burn versus a wildfire. And I hadn't really thought that anyone had used this chemically detailed information to be thinking about the potentially different air quality impacts of wildfires versus prescribed burns. So while we weren't looking for this, it's something that this exact slide got me thinking about. So again, we're kind of trying to just do this detailed characterization because it's important for predicting PM, but really we started thinking about, is there some policy or practice relevance to what we're seeing? And I'm going to talk a little bit more about that in the next slide. So I want to switch gears from just saying, okay, we have all this data and how do we use it in models to start thinking about policy and practice relevance. So when you're predicting emissions and their effects on health and particle levels, you basically have some kind of combustion or fuel, a fire model. And one of the things that fire model will tell you is the total amount of gas phase organic carbon. Okay. Then in an air quality model, this gets mapped to model species. So we have to take, when I go back, I'm going to actually just flip back for just a minute. When I showed you these plots, every black dot, which you can't even see, here we identified 400 compounds, but there were, thousands. We could only name about 400. We cannot possibly represent all of that in models. That's one thing I should have said. So these individual species actually get mapped to model compounds, and they only get mapped to a handful of compounds. So then what happens is these model species go on and they do chemistry, gas phase chemistry to represent the reactions in the atmosphere, very simplified, and then an aerosol formation model that represents that gas particle partitioning. Okay, so we've been working in this space where the total amount of organic carbon is provided by some kind of burn model, and then we're using our detailed measurements to map to these different model species, okay? So we created this new emissions inventory. And one of the things is that this was allowing us to take the detailed information, such as the information that we've been gathering, but these kinds of studies are happening more and more often. We have all this advanced instrumentation. And so how do we take all of this new data that are out there and really use them to do better predictions? So we've created this NEVA database. I'm not going to go into the details. I don't really have time, but we wanted to incorporate this detailed VOC information and allow a bunch of user flexibility. So one of the things that I'm going to show you is that in our database, if we look at one forest, this temperate forest, we now have over 500 compounds represented for this type of fire. So temperate forest would be similar to what we would experience here. Coniferous forest would fall under temperate in a global model. And in this base database, there's only 100 compounds. Now, this is showing that total non-methane organic compounds. And what the importance of this is that we're not adding mass to a model, but we're actually changing the composition because we're adding new information. And the reason that this is important is because it will change the predicted chemistry. Okay, so one other way to look at this is that we've taken now these 500 and some compounds, and what I'm showing you here is I'm showing you those compounds mapped to their model species. So again, you can't read these, but what each color is showing you is one model species. This is a very commonly used database in the middle. It's from 2011, and it's showing you the relative fraction of each of these compounds, model species. They're not actual compounds, but they're model species. And then all of the mass that they knew was there, but they couldn't identify what it was. This is a recent emissions inventory, 2018. And then on the left, this is our inventory. So we really now only have a very small fraction that's unidentified. And if you just look, you can see that these colors are different, they're relative amounts. And again, the reason that's important because number one, it will change the chemistry, including pollutant information, as I've set up above. But the other thing is that this distribution will certainly change as a function of combustion conditions and fuel types. and that these characteristics are different for wildfires and prescribed burns. So I only have 2 more slides. I know I'm at 15 minutes here, but what we wanted to do is then use a 3-dimensional model to predict pollutant levels, focusing on PM2.5, you know, for wildfires versus prescribed burns, and try to understand these policy and practice relevant levers. So the fact that the emissions may change depending on what part of the fuel is burning, or how hot, how fast the fuel is burning, you know, what are the implications for the levels of pollutants that are formed, and how does that inform perhaps, you know, how burns are conducted, right? Or maybe when burns are conducted. So I'm showing you now some of our very first results from the 3-dimensional models. And one of the things that I thought I added here, but I didn't, okay, is that, you know, the very first thing we have to start with is actually understanding something about the seasonality meteorology before we actually get into the chemistry. So this very first modeling exercise that we did is we took a single wildfire season in Northern California, and we modeled the PM2.5. This is a 3-month average seasonal increase in PM2.5. And this is for the wildfires. They happen largely in June to August. And then we said, okay, what if instead of that burning as a wildfire, it burned as a prescribed burn? And so it had to burn during a time where the moisture, fuel moisture is at a certain level and wind speed is a certain level. So this moves the burns into different parts of the year. So this is just sort of a hypothetical exercise. This is not exactly at all how prescribed burns work, but we just said, okay, this is one way to do it. And so you can see that a couple of things, well, we've moved the burns on purpose to different times of the year, but there is actually a change in the amount of PM2.5. So these are some preliminary results that we're looking at now. And just to wrap up, there's, you know, this is years and years of work, but what I want to highlight here is that, you know, the complexity that we capture in our measurements is typically completely lost in models. But we've been building these tools to allow the representation in air quality models because I think that's important for getting accurate predictions of the PM levels and also developing policy, you know, understanding the policy relevant levers. We're using the observations in the differences between fire emissions to explore whether these differences are useful for optimizing prescribed burns, right? So for planning purposes, for how the burns are conducted, and that we're modeling the differences in the distribution of these pollutant levels to identify, again, these policy and practice levers. And I know that was a lot in a short time, but I'm going to leave it at that. And thank you for letting me share some of the things that we've been working on.
Excellent. Thank you, Dr. Barsanti. We do have time maybe for a question if somebody would like to put one into the chat. Yeah, David asked a question that I was going to propose as well, which is, I know you and I talk about these questions all the time, but if you could comment a little bit on, in terms of kind of the end products, the end results that our work might provide in terms of optimizing these types of practices. Like what would be an end scenario where we'd be able to make those kinds of positive contributions to the decision-making progress?
Yeah, so, you know, one of the things that I don't think is okay, so in a policy sense, when a wildfire happens, the PM levels they don't necessarily count against you in terms of violation of the Clean Air Act. Okay, so PM2.5 levels from a wildfire don't count against you for the Clean Air Act. You're able to subtract those because they're natural. On the other hand, when you have a prescribed burn, that's a man-made fire, counts against you from the perspective of the Clean Air Act. So I think if we could, we don't know, I mean, we don't know what we're going to find, but if indeed there's a way to have lower air quality impacts by carefully planned prescribed fires, I think that maybe there's a chance to influence that kind of thinking, that prescribed fires need to be counted against you from a health impacts and wildfires don't, right? That we, because at the end of the day, people are experiencing these levels, So I think that's one thing. I think actually, but I also like the idea of trying to, I think it's important. One of the resistances to prescribed burns are health effects. So, can we, if we find something, can we, I think from a policy perspective, change some of the requirements about prescribed burns, again, based on sort of these optimization of you want to minimize fuel loadings and reduce the health impacts. So I also think about, how do we protect human health in these times? One of the things, again, like Will and I were talking about is, can you provide resources that allow people to stay inside during these times and keep their windows closed? So if we understand something like about the seasonality of exposure, can a policy relevant, when I think of a policy relevant, I think, providing loanable air conditioning units in impacted areas so they can close their windows and doors. And I think that's just understanding the timing of pollutant levels. There's some sort of things that I've been thinking about. But at the end of the day, this is fascinating from a chemistry perspective, but after working on this for over 10 years, you just start to feel like we have to find something that has some, that we can push a lever, right? That we can affect some change to protect people, because it gets a little bit depressing, to be honest.